hardware treats them identically. They're just tasks. They're just bits of code that users basically run. And it's just just scheduling. Is done in all of the scheduling. In fact, in Linux is done exactly the same. Threads are scheduled exactly as processes. And this serial process just happens to have a single thread. So the sort of default behavior of processes is you have one thread, you're a thread, and it's scheduled like any other. Some confusion, not so necessarily confusion, but one thing to remember is they can run on any processor or any core. They can migrate. They'll tend to stay in the same one. There are benefits to that, particularly keeping your same cache. But eventually they can move. And so you can't make necessarily any assumptions below the hardware level where your thread is, unless you hook into the OS to make sure it doesn't get swapped to another processor, because we're not going to worry about that. So the two sort of, where they diverge most obviously is the separate memory versus the same memory space. Threads all run in the same memory space and share everything. Processors really share nothing or share very little. Okay? So multiprocessing, you've got separate processes. They're running the same code usually, and in fact often are running exactly the same code in C or in Python, regardless of what it is. But they have separate memory spaces. Once the two processes split, they have their own copy of everything, and writing to one variable in one space doesn't change it in the other. They have separate file handles, separate everything basically. Just two unique individuals. Threading is in the same process. Same code, same memory, same variable. So a Python thread that changes the variable, and any other thread in that same Python process sees that change. Okay. You'll often hear threads referred to as lightweight processes, or processes referred to as more heavy than threads. And that being, a major difference. And starting the process versus starting the thread does involve more work, right? There's more state in a process than in a thread. The memory pointers, basically when you create a copy of a process or create a second process, you need to set up its memory, set up its code space, create the registers, get the registers all cleaned up and everything. The processor's thread state already. And so there's a slightly more overhead when you create a thread, or create a process versus a thread. And there are obviously some caching costs, because now they're going to be referring to different parts of memory that have very similar data. But actually in Linux and OS X, a process is very close to a thread. They do some tricks with the memory mapping to basically make it almost exactly the same cost. Not quite. It's a little bit overhead, but especially if you create a new process, like copying an existing one, any memory that you don't change in either process will remain shared. And so there's no real cost to having that memory. In Windows, it's different. Windows processes are much more heavyweight than threads, at least in all the documentation I've seen. And this is just more historical. There's a much heavier emphasis on threaded programming in Windows, taking advantage of threads. Threads are typically, or are literally, much more lightweight. So under Windows, this isn't. But most of you are on Macs. A lot of you are going to be using the cluster or other systems like that. So we're just going to assume that we're on Linux or something like it. And the heavy lightweight distinction is not really, relevant. Yeah. So the weight of this part, in terms of, is based around, how difficult is it to create a new process versus creating a new thread? How difficult is it to, what does the OS support in terms of thread communication primitives versus process communication primitives? What about scheduling? How are threads scheduled versus processes? In Linux, it just treats basically processes and threads are the same thing. It's just that a multi-threaded process is just multiple threads versus a single thread. But the threads are what actually is scheduled and exists in the low-level OS. And there's been the emphasis that they should be basically this. So from this separate, share nothing, share everything economy, is from a programmer's point of view where the biggest differences lie. Because in a multi-processing system or approach, you'll usually use message passing. You'll send messages between processes. They'll talk to each other over some communication socket or file. Threads have shared memory there. They're in the same memory space, so they can just use shared variables. Right? They can just use the same memory space to communicate, but that requires locks for safety. We'll talk about what that means and what happens. So communication, multi-processing. You got separate processes, so you communicate by pipes, which are basically just special files in the operating system. They don't necessarily have anything on disk. When I say file, they just have file-like behavior. You write to them, you read from them. One process can write to them and then just introduce them. But that also means that data, since you don't have shared memory, anything that's in data, if you have an array of values or an image, you have to serialize up, you have to convert that image to a representable format that can be written to the file, or the file-like object. You have to convert it, write it, read it on the other side, and deconvert it. So there's some overhead costs. Threads, on the other hand, you've got the same memory. You've got an image, you want another thread to see it, it's there, they see it. They communicate via shared variables. They use locks to ensure safe access. I want to talk a little bit about locks because it's relevant to the discussion we'll have Monday, the discussion that's been going on in Piazza. What is a lock? A pipe, no, it's Unix terminology. A pipe is a file object that doesn't actually have to go to disk. It's basically it's something where you can write to it like a file, and if something else, including yourself as a process, reads from it, you get that data out. So it's a file. It's very efficient, and it's just a way for processes to communicate. And it's just that, it's just a FIFO that has two ends and can be seen by multiple processes. Is that clear?
Is it the same with message queues or is it something inside?
It can be implemented with message queues underneath, but it depends on the OS. It's up to the OS to implement. So the implementation underneath, you could actually just write the disk and have something read. That's not done. It's inefficient. But there are many choices there. Usually just a memory buffer and some sort of blocking primitive underneath in the OS, so that multiple readers or a single reader, a reader and a writer can attack it at the same time, or can deal with it at the same time without problems. All right, so a lock. We'll talk about locks more later, especially when we get to multi-threading. We need to have at least some background so we can talk about them on Monday. And so this context, the difference between multi-processing and multi-threading makes sense. This is a special type of variable. It's got some OS support underneath. And basically it has two things you can do with it. You can acquire the lock, you can pick it up, and you can release it, you can give it up. But it can't be acquired twice at the same time, that's why it's a lock. So if another thread comes, if you've got the lock, if one thread has the lock, and another thread comes and tries to acquire that lock, it has to wait. It might be able to check whether it can acquire it without waiting, and go and do something else. If not, but if it tries to acquire it, it'll wait until that lock is released, and then it'll get it, and then it'll have to proceed. Okay. All right, the most famous lock in this class, the GIL, the Global Interpreter Lock. In Python, only one thread can be running interpreted Python code at a time. That's enforced by the GIL. So anytime anything wants to evaluate a statement in Python code, has to pick up the GIL, evaluate the statement, and then later on can give it up, usually sometimes later. And so technically all variables, all Python variables in pure Python code have an implicit lock. You can't have two threads accessing the same variable at the same time. But that doesn't mean that you have thread-safe code. That's something different. We'll talk about that in a sec. Basically, you have to assume that between statements, that lock can go away. And in fact, it's even finer grained than that. It can go away in steps of the interpreter that lives underneath, which operates on bytecode. So if you're our multi-threaded code, which we'll be writing later, two threads can come into any place, any time, and operate interleaved. For some examples posted by Delete on Piazza, especially. Where are they useful? Let's talk about a lock example. We're going to write a three-thread application. And we want to write to the same variable. Remember, we're in a shared memory space here, so everything is working the same process. We have a driver that's going to put work on some queue, some list to be worked on. And then just two workers that just take work from the queue, from the list of jobs, and do it. And then take pass off the list and then work on it and then go on. Okay? From the worker's point of view, here's the very simple work queue. I want to get a job to do, this is what I do. Right? I have some work list, I'm not going to worry about the driver code for now. I have to declare it global so that I can modify it. Basically take a job off the site, set the rest of the work to be done to the rest of the list, and then return that job. Some work to be done. If I have multiple threads possibly accessing this function at the same time, what can go wrong? Is that the next slide? What happens if multiple workers that try to do this at the same time? Will it work?
One thread can grab the element list, and the second thread, and before it resets the work list, the second thread can grab the first element, and then the first thread will reset the work list, and the second thread will reset.
Right. I'm going to write that out. That's good. That's exactly correct. There might be more subtle problems. That's perfect. So I've got some work list. Right. So in the perfect world, worker 1 will come and take 1, and then the work will be this, and then worker 2 will come and take 2, and the work will be 3. But if I have 1, comes in, grabs the first, right? Sets what's called job. Basically sets that to 1, right? And now wants to take that 1 off the front, but stops right there. And now worker 2 comes in. We're multi-threaded. You can have to stop at any time. So worker 2 now gets to run. This is where worker 1 paused. What does worker 2 see as the work list? Right. Same thing. And then worker 2 says, okay, I'll now set the job list. Work list, what are they called? Work list. Right. It basically goes here and says, okay, do this. Right. All right, so now they got the same job. That wasn't good. And then this one might continue, and now it'll set even better. Right? And now job 2's gone. Never run. Job 1 is run twice. Everything is horrible. Okay? Why did worker 1 stop? So scheduling. Worker 1 stopped. Sorry, I should have said that before. When you have multiple threads on an OS or within a process, they run for a while and then they stop running. Sometimes they'll stop running because they're waiting for files, or because you can actively give up. You can basically yield to, say, in C and various other things. You can just say, I'm done for a while. Let someone else run. To make multiple threads work together, the Python interpreter runs each thread for some amount of time, 500 instructions. I forget what the actual numbers are. Runs it for some amount of time and says, okay, your turn is up. And that turn can stop, at any time. You can usually assume that it'll run for a while if you're doing computation, but there's no guarantee. Especially if you've got other things flying around like interrupts. It can happen at any time. So the point is, if you're multi-threaded, don't assume that just because you're executing statement 1 that statement 2 happened before something else has gone and happened in your process. All right, how do we fix this? Well, let's talk about what's critical. This is a term that's worth knowing. Critical region is basically parts of code where having two threads in there at the same time is bad. So we have a critical region in this code right here. or we're manipulating the work list, or we're taking the value and assigning it to the rest of the list. We need to protect that with a lock. It's really easy in Python. We just do this. I'll show it. Literally, we can just create a lock this way. It actually probably is multi-threading lock. It's locked, but yeah, that's the default. We just have this with lock. This basically says, for this block of code, acquire the lock. When I leave this block of code, release the lock. So now, only one thread can be in there at once. Right? If one thread goes in there, gets the lock, it gets to finish all this before it gives up the lock. If another thread, if the second worker comes in here, tries to get the lock, it has to wait. So this is in the multi-threading. I needed to go a little bit in the threading to talk about locks. In a multi-processing example, you would have to create it. We'll talk about that. I'm going to run some multi-action. I'm going to switch to just multi-processing in a minute. And in that case, you would need the lock before. Threading, you don't fork. So if you create the lock, whenever you create it, the other threads can see it, right? So as long as the lock exists before I define this function, so that it's referring to it, or nodes, I mean, it doesn't even have to be that order. As long as before I call it, right, it's fine. This is just because we're in a shared memory environment. Any resource that one thread allocates or creates, another thread can use.
I guess how would you set up multi-threading by the
We'll talk about that. You can actually just look at the threading module. The documentation has examples. It's pretty good. And it has logs and shows how to use it. You can run something very much like this. And if you fake up some, if you put a sleep here, an example without the log, you can basically force a context switch and show this bad behavior previously.
Can you use this with Spark? Or is just Spark not compatible with Locker?
You wouldn't need to in general, right? The Spark is sort of a data flow paradigm where everything is immutable, so there's no worry about overriding things, right? That's how Spark is
But if you're keeping an external variable in, say, an iteration in your homework, the external variable is Python. It's not.
Yeah, but it's not visible to the workers. So the workers in Spark don't share the state.
Oh, okay.
Right? They're off someplace else, and all they see are RDBs. And there's communication that does that, but there's no shared variables or shared states that needs to be protected. There are some. Well, there are. There are accumulators. There are. That's really it. Because most things are not writable. Really, the only thing you can write to in Spark by default is an accumulator variable, and it already has protection for those. They run in a single worker, and it's single threaded in that single worker, so it doesn't need to worry about it doesn't have to worry about conflicts in that single worker, and then it has the multiple workers, which are separate processes or even separate machines, and then those are combined state. So there's no real need there, because that's partly because of the immutability, right? If you had the ability to modify RDBs and have the ability for shuttles to modify RDBs in place, then you would have all kinds of ordering problems that you have to start talking about laws, but it just takes care of that. But this is sort of a different paradigm. It's the data flow immutable sort of things can only be changed, only be created and never modified. Other questions? All right. So, just in summary, are locks clear? We'll talk. I want them to be clear because Monday's discussion will involve.
Can you define sort of the global variables in such a way that each thread only writes to a particular portion of the variable?
Yeah. So certainly you could, you can get a thread index,
Yeah.
and you can have non-shared state, and that's an approach we'll talk about when we talk about threading. The best way to write multi-threaded code is to not involve any, minimize communication and interaction as much as possible. So separate up where if you've got an embarrassingly parallel problem, right? That doesn't
example where we're kind of reading and writing together, and it's like, well, why don't you just read and write from individualized portions?
So yeah, you could do that. The problem becomes, okay, what if I don't know beforehand which portion takes a lot of time?
Right.
Things like this. So yeah, that's certainly the easiest ways if you don't have to actually communicate. You can just use multi-threading or multi-processing without any sort of overhead, right? And just run parallel processes. A lot of problems can't be crazy, and so the trick is trying to figure out how to minimize that overhead cost and make it. Okay. Anything more on locks or what the differences between processing and threads?
The threading module in Python gets around mobile interpreter.
Threads still run the multi-threaded Python processing. Multiple multi-threaded Python programs still have to kill. Only one thread will be an interpreted Python at one time. And you can have multiple threads; it's just they'll be doing other things. Now, this can be quite useful even with that, because if you've got something IO bound, you've got a bunch of threads reading, crawling the web. So they send out a request, they read back data. There's a long time there where something else could be done.
Like that only one can be run at once.
Running at once, but that doesn't mean that you can't be doing, right, when I'm doing a web request, I send off the request, and I have billions of cycles before I get an answer back, right? It's going to be seconds. If I'm crawling up a bunch of web pages, I can launch a bunch of requests on different threads, and then those threads just sit and wait for an answer to come back. And whoever gets an answer can then continue. We'll talk about what's actually going on in threads.
You know, there's a difference in speed between blocks like that and like synchronized
We'll talk about queues in a second. You mean like the queue object?
Yeah.
They use locks underneath.
Okay, so it's the same.
It's the same. It's just rather than having to, a queue is such a typical object. We'll talk about it in just a second, actually, because you have the multi-process team as well. It's just such a helpful little thing that they just implemented. But underneath it uses a lot. It's going to be efficient and it's going to be tuned to work well, just because everyone's going to use it. But there's no All right, so let's talk about the actual multiprocessing, how to actually do multiprocessing in this pipeline. Here's an example. Assume I want something, I want some interactivity, but I want to go and do something that takes a while. So I get the multiprocessing module. I've got some function that I'm going to do in another process. And this is all I need to do to create that other process. Processing, process. And the target is just do this when I start you. Now I'll create another process, go and evaluate the code. Give me that's not a Python shell. That's a Python shell. Okay. So I can still be typing here. Interacting. And then it comes back with the whole run. So sleep for a while, just turn back. And there's something subtle here. When you start a process, it's standard out, that special file that it can write to that produces output on your terminal is shared. So anything you print out in a separate process will appear in your terminal. Right? But that's the basic thing, that's it. I can look at what P is, what's P? Process. Stopped, if it's finished. Look at, what kind of call it. Is it live? No, it's not. If it were still running, I'd get a truth here. I can check whether or not it's, I can check all kinds of things. I can see, I can check. You can read the multiprocessing one, but it's just an object. It talks about another object, it talks about a process that's on an operating system somewhere. That's the basic idea, right? You create a process, you tell it to do something, it goes and does that thing, comes back later. How do you get useful work out of it? The two sort of basic begin and end functions are start and join. Start just starts the process, calls its run method, sends it off on its merry way. If you created it with this target equal function, then run just calls it. if you want to do something more complex, you can do some object-oriented programming in Python. You can inherit from a process, override it, start, or run the function in whatever way you need to do more complicated things. There are various other options for processes here that you can look at this to help for the process object itself. Get an idea of what you can do with it. And join is then just you use it to collect it processes. This happens automatically in some cases, but it's good to do it explicitly. Basically, any process that you start, you should later join, just to make sure it gets cleaned up. In Unix systems, when you create a process, the parent process owns that is in charge of that process. It can't actually exit all the way until the parent process says it's okay. So it'll just hang around consuming some resources until you actually call to it. Python tries to clean up most of that, but not always. So it's good to be aware. And it's good practice just to always do it. Okay. Process pools. So you have 4 processors, or sorry.
So it's possible for a child process to possibly spawn
To spawn a parent, it can spawn another child, but it can reparent any process. I'm not sure that it can change each parent. If the parent dies, then it gets reparented by process 1, which is just the default. I don't even remember what it's called. And then that process is responsible for collecting. But in general, no. You can get a hierarchy of processes, but you can't stick with breath. That would be that's some time travel stuff there. So process pools allow you to create any workers at once, and then you can serve them jobs, have them do work using map or apply, and a couple of other variants. Those are the 2 main ones. So map. Everyone knows map just from Python, or this known from this from Python. It's exactly the same thing. Let's got a simple example here. All right. So I'm going to do a little map example. The worker is just going to sleep for 1/10 of a second, and then increment its argument, and that will be the result of the map. And then I'll create some workers. So I'm going to run it on range of 20. So in serial code, this will take 2 seconds to finish, right? Because I'm sleeping it for 1/10 of a second. You're right. So let's do this. No, so am I actually. I'm glad you bring that up. I mean, I'm not, got plenty of characters left in my fingers, hopefully, so I should use longer characters. All right, so I create a pool. I can actually, you'll see what it is. It's not actually doing anything yet. There are no processes running. Or actually, no, maybe they are starting. I'm not sure if they're starting right away or when I first do some work.
That the pool command, is that your message that like you have full workers?
Yep. Yeah. I basically. Oh, yeah. So it's basically give me 4 processes.
Okay.
And we'll see that.
Is that
So
the
this.
same as workers? When you say
Yeah, workers process work. So the typical Unix model is the parent is lazy and the children do all the housework. So, and that's you'll see that. And if you write it in the other way, it's perfectly valid code to write something where you spawn a child and then you do a bunch of work and you hand it off to the child to do with. But almost always it's the other way around. Parents are lazy, and so you spawn a process. It does a bunch of stuff and then goes away. Okay.
Yeah, I mean, in this case, the parent is parent.
So the parent is actually the IPython. There are 5 processes now.
Okay.
There's the one that happened before. There was the process that already existed before I created the pool, and then 4 more. And so when I created that pool, now there are 4 other processes. They're just waiting for one. So let's send them some more. So I say, okay, well, let's map the worker function onto the range 20. You can see that it used to start with 0, now it starts with 1. It came back faster than 2 seconds. And if we look, since I've got multiple print statements there, took about 600 milliseconds. So not quite 4 times faster than it would have been with the search engine, but reasonably. Any predictions for this? Sorry, question first.
Never mind, Sorry.
Okay, predictions for how long this will take. So 20 to roughly a quarter, right? 4 workers next to this. What's that? Not just over the chunky, right? When I run this, it's going to take about 30 to 4 of this. Why? I only have 10 objects and 4 workers, so 2 of the workers will be free, 2 of the workers will be 2. So the longer workers are dominant, right? Make sense? Because I've got a small job. There's a trade-off here, right? This is like problem 2. Which is the matter of 1, 2. Problem 2. Balancing work, right? You're going to be dominated by your most expensive task. In this case, it's applying this to free instead of 2 objects. The map function actually takes the range and evaluates it, and then chops it up into equal-sized pieces as best it can, and farms those out to workers as a block. It's important to remember that because if you hand it an iterator that doesn't end, or that has some expensive memory or something like that, it'll do not what you want, which is evaluate first and put it in a list and then chop it up. The IMAP, if you have an iterator that you want to, if you have something you don't want it to expand, use the IMAP there. Okay. That's all. So the map function has a sequence, takes a sequence, it evaluates it into a list. So the first thing it does is it turns that sequence, whatever its source is, into a list, and then chops it up into equal pieces and sends those out. You can control the size of the chunks, but be aware that that's the first thing it's going to do. If you want it to be more, feed it things one at a time, there are other ways to do that. There are 2. There's also the async variants for map and for apply. Map just waits for the result. If you launch it, it sits, when everything's done, you get the value back. Map async, it returns immediately. It's a non-blocking version of send work off. So it returns something, it returns a result type, and you have a method to get there. And that result also has rating and weighted. If the work is not done and you call get, it will hang until you do get the weight. But it allows work to be started while the driver or whatever the parent process continues along doing other things. So we can see what that looks like here. So exactly the same worker. Basically everything's the same as the previous example, so let me use map async here. So I set it up first, and then I have here a map result object. It launched the work, it's often done, it's already, the computation is done. I don't have the result here yet. So to get the result, I need to do a little bit more work. So what I'm going to do is I'm just going to put a busy loop. I'm going to launch the work, that map async call, and then wait for it to be ready. And then once it is ready, then I'll actually get the answer. So, launch the work, waited 3 times, so the 300 milliseconds we saw before, and then the work is done, and then it could get the answer. Clear what happened here? This is async means the driver doesn't hang. Clear? Not clear? In fact, the map function is just a wrapper for map async. It calls map async on the thing, and just immediately calls get. So it waits for the answer and then returns that to the calling mode. You can, it's worth actually. You can pull up the multiprocessing.py code and look at it. It's not that complicated. It has some low-level stuff in the process itself, but the map functions and all these are pretty simple.
When is the situation when you launch it? Like when you try to do it? When would you want it?
So if the driver is, for example, getting chunks of work, like it's got, you know, it gets blocked of work from somewhere. You know, I think it's like 100 URLs from a file and wants to go and crawl those. Right? I get 100 URLs, I map them to something that goes and fetches the page, and then I start getting more URLs. I want work to start as soon as I've got something coming in. Right? Where the driver is being, the driver has other responsibilities. You know, for example, it's interacting with the user or something like that, and launching work that's expensive and requires multiple processes. Anytime where the driver is going to want to do some other things or be responsive, or if it can launch work in parts, but getting those parts takes a long time.
So like you want to start the work,
I want this-
does not hold the name of your parent.
Right, exactly.
You're doing something else in between, and then years later you wait to start it.
Exactly. Okay. So basically, anytime I've got, I know I have some work that needs to be done. I'll start that work. I'll go and find what other things I need to be doing, and I can use the pool. I can launch. You know, I'll get this result type, but I could just launch some more work and get another result type and just hang on to those, right? And I could sit there. I could, you know, launch 100 of these. Some of them might be very short. Some might be long. I can just check which ones are ready.
Or you can tell like how many are finished.
Yeah, there's that ready, result.ready.
Yeah.
I'll post these, but result.ready tells you whether or not it's done. Once it's done, then you can go and get it. Right? So I could launch a bunch of these maps, store in a list basically the results, which are promises for future values. Right?
I thought you meant that you could tell which of the workers in a map.
Oh, no, it's the map. It's the entire map. The entire map is gives me a result. Same thing with apply. So the more likely case is to use apply async, because apply launches one computation into the pool. Whoever is not busy will take it. Right. So this is maybe more likely. I'm not usually, if I get work, I'm usually going to get like 8 tasks at a time. I'll launch that, and then I'll just say, okay, so usually I'll get one task, I'll launch it on a async apply, get a future, basically something I can use later to get the result. And then later on, when they're ready, I'll take it next. But I don't have to hang around waiting for it. Is that make sense? Okay. Good.
Yeah, so the map you work one number by one number, or it gives like the number of steps divided by 4 and you like store things like four.
So the question is, how is the map dividing the work?
Yeah.
So you can control the chunk size. There's a chunk size argument to the map function. And you can say chunk size should be 1, and then it's 1 by 1. Or you can, or if the default is to chop it into contiguous pieces the size with the largest possible one chunk per worker, which might not be the most efficient if the work involves different amounts of computation. So it doesn't do 1 by 1 by default. It does. So for 10 with 4 workers, it goes 0 through 3, 4 through 7, 8, 9, and 3, 3, 2, 2. So 0 through 2. Sorry, 0 through 2, 3 through 5. But you can control that. It's in the map async function, actually. It's great to look at, but it describes it in the documentation. The map function is called map async, and then calls skip. I think.
Wouldn't you always want to run this in Cython so you can use multiple cores processing?
I'm using multiple cores. So multiprocessing takes advantage. So as soon as I have multiple processes, it drops down to the OS. And this is the same for threading, actually, too. As soon as I have multiple threads, it drops down to the OS. In this case, I don't want, got minimal communication requirements, basically. But those processes are all running in parallel, which is why it returns faster than, rather than taking a full second, it takes about a third of a second if I make that one.
Okay.
It's because those are running, if I looked at my processor output in the
I thought Python only runs one process at a time.
So that's exactly correct. This one is instantiating multiple Python processes and talking to them. So it's basically, there are 5 actually. There's the IPython and then 4 workers. And they are running as separate processes, just like I started. I could start them up. I could have done something where I start them up on the command line and use internet connections to talk about work, but this is just an easy, transparent way to do it.
So then there's 5 processes with 5 guilds?
Yep, 5 guilds, 5 separate guilds.
There's no like.
Which means that they can be in the same, but they don't. That means also that they don't share anything really. So there's no collision if they write to the same variable, or this is not a problem. But then I have to use other communication methods for them to talk to each other because they don't have any shared state.
So if threads are running in parallel on different cores, how does the shared memory work? I'm guessing they all have their own caches on different cores, right?
They don't. Well, so the different cores do. So
Right.
caches are a hardware thing, right? So when there are multiple threads running with the same shared memory, what that means is at the bottom, the RAM, they address the same RAM. So if there's a value, and the cache is just a proxy for the RAM, right? It's just a faster way of seeing what's down below, but it's still what's down below. So when multiple threads access something, if it's in cache, they get it very quickly, right? So if they're looking at the same value over, then one thread will look at it and see it in cache and say, okay, I'm happy. The other one will look at the value that's in cache, I'm happy. If one of them writes down to memory and then a long time later the other one runs and reads from that memory, it will see what's down there. But it's basically down at the bottom, the memory they see is the same. So all the variable names and all the pointers that are involved underneath the point to the same. That will become more obvious when we talk more specifically about threading.
It just seems like you'd get a lot of dirty bits in the caches, and there'd be a lot of
So
checks if you're updating.
Yeah. So you can certainly. We'll talk about false sharing, and if you want to search for this false sharing caching, we'll talk about this where it's especially bad if they're on separate cores and one is modifying data and one's trying to read it. Then it has to. If they're on separate cores, that forces this other core to go to that cache to see what's dirty, or this one has to write all the way to memory, which is slow. And so if you get in that sort of behavior, it's horrible. Yeah, it's really slow. If you're just reading, then it's not too bad. Although then if they're sharing, they still have to make sure that they're both not modifying. That's sort of future proof, all right? Is it clear? What's going on here? Separate guilds, separate processes. Their work is launched, but it runs in parallel. There's no sort of collision because they're just running off independently. All right, I don't think we're going to get to queues and pipes in the queue example. I'll post it. You can look at it. We'll go through it very quickly before or maybe after the reading discussion on Monday. So Monday we'll do the actual deal reading discussion. Keep posting there. If there are questions that haven't been answered in the thread or that you just were reading through and you found that it was interesting, make sure to bring those on Monday. We'll do a little more multi-processing on Monday. We'll finish up what we're going to get here, which are basically queues and pipes, and how you actually can share memory processes and things if you need to. And then we'll go from there. All right. Have a good weekend.